Here we have an example of an OR statement. So we see two separate inequalities separated by the word OR. To solve an OR statement, you want to solve each piece individually. So in this case, the left-hand inequality, I would first need to add 13 to both sides. That would yield 2x, the 13s would cancel, and then on the right-hand side, 13 minus 0.8 would be 12.2. Now divide both sides by 2, and we would get x is less than 6.1. Now, at the end, you want to make sure that you keep the OR that was in the original problem. Now go back up, and we want to solve the problem that was on the right side. So we have 2x minus 13 is greater than 0.8. So we'd want to add 13 to both sides. Doing that would yield 2x, 13s would cancel, is greater than 13 plus 0.8 would be 13.8. Divide both sides by 2. So that would yield x is greater than, and then 13.8 divided by 2 is 6.9. So we have a final statement that has OR in between each one. Now, anytime that we're asked to solve an OR inequality, you really need to graph, no matter if the question asks you to graph or not. So we'll have 0 on the left, 6.1 to the right, and 6.9 to the right of that. We have x is less than 6.1, so a parenthesis, and the graph would go to the left for that one. And then x is greater than 6.9, so a parenthesis, and then to the right of that one. Think back in the lecture notes in the place that I told you about OR statements. I said there are 3 different possibilities when you have an OR problem. This is like the last possibility, where you have your graphs going 2 separate directions, but you have a middle part where you would have no solution because the 2 graphs are not overlapping. And so this particular one, when you combine the graphs, ends up being just the 2 graphs unioned together. That being the case, the interval notation would be negative infinity to 6.1, parenthesis, union 6.9 to infinity.